Alright, time for another draft. Physics.com, debatephysics.com also, where there's a bunch of 5-minute videos going over different arguments related to the duality, the energy duality of having a formula like 1/2 mv squared and a notion of momentum, mv, as being the origin or the essence of energy in the universe, and that these two definitions really are not in any way compatible, and it just creates really bad science. Anyway, so this is the Stern-Gerlach experiments. This has more to do with quantum mechanics, the invention of the notion of electron spin, the rotation of dipoles, you could argue, something like that. And I think it's kind of obvious that they've overinterpreted the experiment, way overinterpreted it. But we'll see. I did gain some insight into what the experiment actually involves, and I don't really want to play the whole video, but yeah, what the hell. We'll do it anyway, just to be complete. So this, who knows when I'll get to the part that's really important. So it's weird that you have to go all the way back to the 1967. The 60s was big on making these physics videos for the public, and unfortunately they just don't do this kind of stuff anymore. There's no educational physics that doesn't have an agenda, or somehow it's all proprietary knowledge, or somehow they have to own it, or all this bullshit. So this was financed by the National Science Foundation, and it's an MIT produced video.
If you're anything like me, your intuitive notions about magnetism are partly right and partly wrong.
Yeah, the guy's intuitive notion of when the camera's on was apparently partly right. It's kind of funny, because film was sort of expensive, and this is filmed, and the guy sticks his head in front of the camera. I mean, just kind of funny. Anyway, if you didn't see that, but it was kind of funny. Anyway, so yes, the idea that they should just stick to what we can know well and what they don't know so well. They should just do it that way, instead of saying, well, we're half right and half wrong.
Despite your experience with permanent magnets.
So very clunky permanent magnets, by the way. Why is it doing that? Oh, commercial. I mean, sorry about that. Ugh, too bad. It was a bit disappointing. Yeah, so it's, paid for by the public. It's probably public domain, I would imagine, unless somebody sneakily bought it somehow. And somebody's put it up on the internet, which is good, but they've thrown commercials on it.
Soft iron, Canadian nickel, compasses. Probably never occurred to you that in the free atomic state, roughly half of the atoms in the periodic table are as magnetic as iron.
Alright, so the trick is it's really not as magnetic. It just means that the atoms themselves, the single atoms, are polarized. That is, they're uneven. So they have more electrons on one side than the other side. So they have some polarization. Now I would argue there's some atoms that are polarized in two directions. Where they have an uneven amount in two directions or three directions. So they can be polar. They can have north-south and north-south. Or they can have south-south and north-north. So the configuration of their dipoleness, can have more than one configuration. So yes, half the atoms in the periodic table are not symmetrical, what you could argue would be the simple argument. Any lack of symmetry in the shape of the atom would mean it is a dipole, that it has a lack of symmetry and therefore will be affected by a magnetic field. But they don't combine with each other non-symmetrically. So when they combine, they become very symmetric. I would argue, okay, that if you took any substance that was a solid and you broke it into pieces, into atoms, that you're going to end up with a lack of symmetry. You're going to end up with atoms that are missing an electron and atoms that have one too many electrons. You're going to end up with a bunch of ions. I don't know why exactly I hit that button. Yeah, I don't know.
These atoms are small permanent magnets, as strong magnetically.
So they're just dipoles. They just have a north and a south. That is, they have a side that's more electrons and a side that has more exposure to the nucleus, the protons. That's all it really means. That if you looked at them and the electrons were excreting red and the protons were excreting blue, you could look at them from different angles and they'd look more blue from one side and more red from another side. That's all they need to be magnetically affected.
Considered as a piece of alnico. Using this apparatus, we'll demonstrate the magnetism of individual atoms by deflecting them with magnetic forces.
Now the problem is that yeah, they have this great apparatus, but they don't do a bunch of different kinds of experiments in terms of the magnetic field that they test. And so, instead of just putting a bar magnet on the house, they could use a very simple magnetic field, show you the pattern created, and then you could make comparisons between these different magnetic fields and how they affect a beam of polarized atoms.
But more than that, you'll see, perhaps you already know, that magnetic atoms can't just have any orientation in a magnetic field, an effect that can only be explained by quantum theory.
So that's just nonsense. So he's just saying that, yes, if you put a magnet in a magnetic field, you put a piece of iron in the magnetic field, it has to turn to the field. The field strength will affect one side of the atom more than the other side, or affect it in some particular way, which will cause it to move in a particular way.
An experiment similar to the one you see here was first done in 1922 by Professor Otto Stern and Walter Gerlach.
It says Stern, and he said Schan, but whatever. I guess that's a German thing. I mean, it's called Stern-Gerlach.
Their experiment was with atoms of silver. We'll use atoms of cesium instead, even though cesium metal in its condensed state.
So why, he doesn't state why they're using cesium instead, but whatever. I suspect it's easier to atomize.
And here's an ampule of it. It's just as lifeless magnetically as most things.
That is, it's lifeless because unlike iron, where it has domains and the domains can all shift into the same direction and magnify the magnetic effect, the cesium doesn't do that. So the atoms remain in random conditions. Because of the way they're attached to each other, they can't rotate into alignment.
But before we get on to atomic cesium, let's get straight to the basic question of the magnetic forces involved. What do magnetic dipoles do in magnetic fields? A compass is just a magnetic dipole that points north. So
this is it, and one little interesting bit is this idea that it takes time for the effect to take place, and like everything that gets momentum, when it starts to move, it now has momentum, it's stored energy. Until you take the energy away, that energy is stuck in the system, and it'll end up oscillating because it overshoots, okay, the neutral point. And it would take anything exposed to a magnetic field would tend to oscillate in that field forever, theoretically, atoms, because there isn't any friction.
Sure, it always ends up that way, but if it isn't that way initially, it oscillates about the field direction for a while before friction brings it to rest. If atoms behave just like compass needles, then isolated atoms in vacuum, free of all friction, would oscillate about the field direction forever.
Well, the point is obviously in this scenario, the atoms would be able to move, so they would move towards the field. The field gets stronger. The closer they get, the less they'll start to oscillate, because the field itself will start applying friction.
In our experiment, we're not concerned with the oscillations, but with the net force on a magnetic dipole.
So I don't know why you brought it up then. So you say, okay, so it's this net force on a magnetic dipole, but it's not the force they're going to apply. They're going to try to apply it in an uneven way. So it's not really, I don't know. It's not equatable to the concept of just saying how strong is the magnetic field, because the thing they're really going to fiddle with is how uneven is the magnetic field.
Now, there are two orientations of special interest that we'll look at. We call them parallel or anti-parallel to the field.
Artificial intelligence.
Oh, too bad. Alright, I'm back. So these are Helmholtz coils. And I really never understood exactly what they were creating in terms of a magnetic field, and so that was an insight in the last couple of days for me that really makes this whole experiment a lot more understandable. So maybe I will draw that. But let's just do this a little bit first.
Here's a pair of Helmholtz coils with some iron filings. With current in both coils, we get a uniform field.
Right. Now the thing to understand is those coils are round. Okay, so they're going on through the table. So the magnetic field they're creating, he's showing right in the middle what it's doing. And it's got a consistency in a certain area where it's doing the same thing. Now the thing it's doing, okay, that I didn't understand entirely until, yesterday, yeah, where it occurred to me what's really going on. So let me get rid of this and we'll draw it. Is comparable to when you're going to do some sort of gravity thing, okay, and you consider what happens in gravity if you have a round object, a hollow object, okay, and you're inside the hollow object. What you can understand is the gravitational force, no matter where you are, is the same. So you're not going to be pulled towards a surface, because as you move further away from a surface, you're exposed to more of the surface. The surface area gets larger. That's affecting you. That you're getting affected by. So even though it's closer to this surface, it has less exposure. You can see there's less of the, like if I drew the line through here, you can see there's less surface area that's going to be pulling that way. And there's more surface area obviously over here that has an effect on it. So you'll never get pulled more in one direction than the other direction. So your gravitational potential is always the same. There's no movement, there's no force of gravity in here, because no matter you get closer to a surface, you're exposed to less surface. You get further away, yeah, it's weaker, but you're getting exposed to more of it. And that's what a Helmholtz coil is creating, is the same kind of effect. So if I take this coil and think about it as the two coils together, creating a north and south, and I think about what they're doing the same thing in the sense I could put a magnet in that field, and even though the field has a north side and a south side, the fact is that it doesn't get stronger as I move it this way. So if the magnet moves here, the field, the pulling and pushing is still exactly the same. There's no more tendency to move. So it's kind of stuck in a balance where it could be attracted here. The south pole's attracted to this north side. Well, and the south side would be, and the north side would be attracted to the south side, you know. And those two forces, no matter how close I get or no matter how far I go over this way, are the same as long as I'm in this range, you know, in the center part. So that's how it works, is that there's a definite field, it has a definite structure, but it doesn't have that normal tendency to get stronger as you get closer, to move into it. It doesn't get stronger. So if the magnet moves this way, the field's not getting stronger, so there's no motivation to keep moving. Likewise, if it moves the other way, there's no motivation, because it's perfectly even in terms of the amount of pushing and pulling. The two magnets, well, if you put two magnets in that, they'll still connect. I'm just saying that the field can't pull the same way it would as if you get closer to a north side. It would get stronger and stronger and stronger, and it just doesn't do that inside this field. So I think that's about the best I can do to explain my insight. And play the video. So these lines just mean that all the little magnets being created, all these little iron filings are now magnets, and they're lining up exactly opposite to the two coils, okay, north south north south north south, but they're not motivated to move towards the poles. There's no force pushing them one way or pushing them the other way.
Smack in the center. When we put a magnet in the center, it oscillates about the field, but there's no net deflection in any direction.
So what he means is it's not getting pulled towards the north side or towards the south side. So no matter how uneven you make its position, it still doesn't tend to go in one direction or the other. It's not pulled towards the south. If I give it a little push towards the south, it won't keep going towards the south. I push it towards the north, it won't keep going towards the north. It's stuck in a place where it's going to align, but it's not going to move because it doesn't feel that the force gets stronger as it gets closer. It's not getting stronger as it gets closer, and this isn't getting weaker as it gets further. So it's just stuck in an equilibrium.
Now let's switch it off, on.
So his off and ons aren't in sequence with the lights, which is kind of funny.
Off, on, off, on. So now we carefully set the magnet anti-parallel to the field in the direction unstable against rotation.
So yes, this would say, you'd say it would tend to swing, but because of the lack of motivation, it doesn't flip.
This is the unnatural position. Our intuitions are sort of against it. To be sure, if it gets off its unstable equilibrium the least bit,
it'll flip. But yes, it's kind of restricted. So yes, so as long as it stays really parallel, there's no flipping force. But if he turns it to its side, it probably will flip.
Swing around, so I have to get it just right. It still doesn't tend to translate in the field. Off, on.
So when it's on, it seems that it's got a dampening effect. It's, you know, it's definitely being affected. It's trying not to move. It's almost stopping it from moving because everything is evened. So no matter what it does, it just evens out. And you can see then when he turns it off, it starts to move more because it's the strings start affecting it. So it's when it's out of balance, the strings have tension, they pull it back and forth. So the strings levitating this cardboard are what's causing the motion when it's off.
Or in a uniform field, there's no net force on the magnet.
So net force, he's just saying there's no increase in the force as you change your distance from the source of the magnetism.
Now let's see what happens in a non-uniform field. We'll put current in only one coil.
So this is like creating just the north side of the magnet.
You can see here the field is non-uniform. It's strongest where the field lines are crowded together. We put the magnet back in the stable position.
Now, it's going to do the obvious thing, right? Now it's going to move because there is no balancing pull from the other side anymore. So the two field strengths aren't equal. And so now you've broken that equality.
And it tends to move toward the coil with the current in it.
That would obviously be the north side coil.
Off. On. It moves into strong magnetic field.
The coils are just wrapped in opposite directions. So one creates a positive, a north side and a south side.
Off. On. Off. Now put the magnet back into the unstable position. The non-uniform field, of course.
So there is no north side for that south side to be pulled towards. So understand, now there's no competing field that's competing with the other side in terms of pulling forces, and they're not being balanced. So obviously as the north side gets closer to the south side, it does increase the strength of the field, and so it keeps moving in that direction.
Parallel. It's not so easy.
But in this case it's going to repel because it's a north side coil, it's a north side magnet, so it's going to basically just push the north away. Okay, and it gets weaker as it gets further away, obviously.
Just there. On. There it goes. It moves in a weak field, see?
See, it says weak field. This isn't really about a weak and strong field. Alright. But it's clearly a north magnet facing a north magnet. And so it's obviously that if there's no opposing force, that is, there's no south side pushing against the south side, then yes, the north side will move.
Off. On.
This part is a little bit patronizing. I mean, yeah, we get it.
Off. In a non-uniform field, then, there is a net force on the magnet, which depends upon the way it is oriented. Now, how big is this force?
So that part is sort of who cares. I mean, we just know it's a force, so who cares? But the real point is it's a kind of a monopolar force. You're just putting one north-facing magnet in the game, or one south-facing magnet in the game, and then saying, what does the magnet do in that field?
You know how to calculate it, thinking of the small magnet as having equal but opposite poles at its ends. Then the net force is just the pole strength times the difference of field at the ends. But if the magnet lies along the field direction, parallel or anti-parallel, the difference of field is just the field gradient times the length of the magnet.
So what this doesn't take into account is that all these atoms will line up opposing the field. So if you had a group of atoms, and that they're all going to be same magnets next to each other, and that's why you end up with field lines. That's why the iron filings create lines is because they're basically creating magnets that repel each other. So they can't create a solid substance because this magnet repels the one next to it, and this one repels the one next to it. So that's why there's lines. So you gotta understand they can't turn once they're in a field of other magnets. So if they're in a field with other atoms and they're going through this magnetic field, there's a whole bunch of them that can't do anything because they're already against another magnet that's the same orientation, and they're repelling each other.
Calling the field direction
They can't
D,
flip.
we can say that the force, F, is equal to the dipole moment mu times the magnetic field gradient, dB by dZ.
So this square here, I imagine, is just the r squared. So it's basically the distance is just the r part.
To get a strong non-uniform field, we can use an electromagnet with special soft iron pole pieces.
So this part doesn't make much sense to me, because they're going to shoot this beam through this little tiny part right here in the center. All of this crap over here doesn't make any difference, doesn't have any effect on the experiment. So I don't know exactly what its function is. Now it might create some sort of more evenness in this field over here because it doesn't leak into it, but it seems bizarre. And the fact is the more modern versions of this experiment, they just use a triangular piece, okay, versus a flat piece, and to get the same effect.
Put a cross section like these. This powder pattern shows the kind of field you should get. Here is the iron, and here is the space between. It's strongest, the field is strongest, near the convex pole piece.
Because this is a smaller arc. You know, the arcs have, the surface area is smaller here, tighter than it is over here, so the end effect. So the south field is weak, the north field is strong.
If a small bar magnet is placed in the parallel orientation, it feels a strong net force pulling it toward the region of stronger field. It tends to
So it says stronger field, it just means that yes, the north magnet is stronger than the south magnet.
fall into strong field. Whereas in the anti-parallel case, there's a repulsion on the side where the force is larger. So it tends to move into weak field.
So they're again just saying that we have one, the south side is the weak side, the north side, so they're taking a strong magnet on one side and a weaker magnet on the south side. Now why they can't do that with just two electromagnets at different strengths, I don't know. We didn't see that experiment. Seems to me it would be just simpler to create this effect with just regular magnets rather than this convoluted design of a magnet.
And so if atoms with magnetic dipole moments enter a non-uniform field like this, they'll be pushed one way or the other according to their orientation.
And of course he didn't explain what they'll do if they come in perpendicular to the field. So if they come in perpendicular, I mean, the obvious argument is that the south side is going to be more strongly attracted to the north side, and there's going to be a weaker attraction of the north side to the south side, so it will tend to turn and go towards the north side. But there's no suggestion that that actually happens.
Now in the experiment itself,
And I'd argue it doesn't happen because these atoms are going through this mechanism with a whole bunch of atoms going through the mechanism, which means that they probably are affecting each other. That is, one atom can't flip, without dragging on the other atoms it's going through the mechanism with. So it has to, if it flips, it affects all the other atoms, so it has a real lack of incentive to flip.
we can't just place atoms between the poles of a magnet and measure the forces on them. Instead, we send a stream of atoms between the poles in a direction perpendicular to the field, like this. and observe their transverse deflections.
Introducing the hide and seek from Belrond.
That's really annoying. A lot of commercials. Alright, back.
Here's a schematic of the apparatus. Atoms emerge through a narrow slit in a small container, which we call an oven.
So they heat the source material until it vaporizes and is shooting off pieces. Okay, pieces are flying off at a high velocity because of a rather high temperature. And so you have pieces that are going, they're big pieces going really slow, little pieces going really fast, kind of thing is happening. There's pieces of all kinds of velocities.
Section of them get through a narrow collimating slit. As they pass through the...
So they just turn it into a beam. Okay, so not complicated. They could just use a little hole, but instead they use something they can contract both ways.
Magnet, their directions of motion are slightly changed by the magnetic forces. And at the other end of the apparatus, there's a small detector which can be moved transversely to explore the deflections
So they take a wire and move it across the field
caused by the magnet. We also have a shutter in front of the oven that can block the whole beam before it enters the magnet. And between the magnet and the detector, we have an adjustable shutter. Of course, the apparatus must be in a good vacuum so that atoms can travel from source to detector with negligible risk of collision. Now let's look at the parts of the apparatus.
Would be interesting just to see how many collisions there are in atmosphere. I mean, I'm just curious how much, how often, what the density is. So how far you could travel on average before it would hit an atom of oxygen or nitrogen or methane or whatever else is in the atmosphere.
These two round metal containers make up the oven. We put cesium ampule into the back one. We break it there after it's in a vacuum because cesium is so active chemically, much more active than its near brother sodium, with which you're more familiar.
The assumption that anybody's familiar, but whatever. Just kind of funny. So yes, but he doesn't explain why he's not using silver.
Warm the oven, you can see the heating coils to vaporize the cesium, which fills both containers. Some of the cesium atoms escape through this 10th millimeter slit. Directly in front of the oven slit is this shutter, which can be moved from the outside of the apparatus by hand with a small bar magnet.
It's just funny to see these clunky old mechanical tools and such. But anyway, yeah, the on-off thing seems really useless. Why not just turn the oven off? But whatever.
And now from there, the beam goes through the collimating slit, the jaws of which are made of stainless steel razor blades.
So another point where you say, well, why do you want a long beam? Wouldn't it be better to, have a round beam?
The two other blades fix the height of the beam.
Or even a square beam.
The width of this column
rather than a rectangular beam.
Collimating slit can be set from the outside with a control. The transverse position can also be set from a control so that we can aim the ribbon-like beam of atoms directly down the magnet.
Just kind of funny, before Phillips, screws, kind of a guff screw there, torn to pieces.
Magnet gap. Here's the magnet. The shaped pole pieces are made of wafers of...
Alright, so basically they're inducing the magnetism into the metal. So there's no direct contact between the magnetic plates here and the actual source of the magnetism. The coils are separated outside. and inducing the magnetic field into the susceptible metal.
Soft iron stacked and bolted together. The pole pieces are quite long compared to the gap. The pole pieces slip into a piece of glass tubing that carries the vacuum, and the whole thing fits into the magnet so we can have the return yoke and the magnetizing coils outside the vacuum system. These rather large coarse jaws can intercept the beam after it leaves the magnet, but we'll come back to them later.
So those are just there to close one side of the beam, or so just another slit kind of arrangement where you're just basically saying I want to cut off half of the beam.
The detector is a 10th millimeter niobium wire. When hot, this wire converts any neutral cesium atoms that strike it into positive cesium ions.
Here are the top 5.
Alright, got another commercial. Alright, continuing.
Are collected by this small negatively charged plate. The current in the plate circuit, which is our measure of beam intensity, is amplified and recorded on the y-axis of this XY plotter. The x-coordinate indicates the transverse position of the detector, which is moved by pushing on it. The push rod can be moved from outside through these bellows, worked by a knob.
So they're just moving it side to side. That's all.
The whole detector assembly is covered with a wire screening to ensure that the sensitive circuit really measures the beam and doesn't act as a burglar alarm. Here's the apparatus ready to run. Now, we really made the second half of this film before the first. This means that we don't have to wait around for the vacuum pumps to work, to find and fix all the leaks in the vacuum system, to work out other bugs that always beset every experiment. So here goes.
Sort of an interesting qualification, just pointing out. But yeah, obviously it's a little complicated.
The oven is already warm. The magnet power is off. The detector wire is hot. Now we open the shutter and move the detector across the beam.
You think they'd have a little motor to do that so it would guarantee consistency, but I guess the spinning thing works. So I just love these old, heat sensitive tracers. Really great stuff.
Then it levels off.
Alright, this they kind of drag out a
The
bit.
detector current at the peak is about 10 to the minus 11 amperes and corresponds to about 10 to the 8th atoms per second hitting the detector wire.
But you bored me to death.
There's the beam. One large division on the x-axis is equivalent to a detector movement of 1.3 millimeters, so the beam's about 2.7 millimeters wide.
So now they just waste our time by making it thinner and reducing the amplitude.
If we go back to the center of the beam, we can insert the shutter and cut the beam off. On, off, on. Now, just to show that we know what we're doing, we'll narrow the collimating slit. This, of course, should make the beam narrower.
So same thing, just now it's just a thinner beam, okay, smaller amount of area where you're in the beam for the wire. So the wire spends less time in the beam.
There it is.
Yes, well, that's something. It's beautifully symmetrical, I gotta say.
Now we'll begin the main measurement,
Good.
leaving the beam narrow. First, a clean trace of the beam with a magnet current still off.
So they aren't deflecting any of the dipolar atoms with any magnetic field. They're just shooting the beam through and getting a beam.
We turned down the gain of the detector a little bit, but that doesn't matter.
So now we're talking about 1 millimeter. I think by his previous calculation, this is about 1 millimeter. Millimeter of space in the beam. Wow, I really have to download this. Yeah, video didn't have this many commercials last time I played it. Ugh.
Next, we move the detector back to the middle of the beam and get ready to turn some current on in the magnet. The field intensity with one cell of this battery will be about 2500 Gauss, and the gradient, which you remember is the important quantity, is about 3300 Gauss per centimeter.
So he's just basically saying, look, we're going to go half power and then we'll go full power and blah, blah, blah. So not that challenging.
The beam intensity in the middle falls. It's a little less than half its former value. Those atoms must have gone somewhere, so let's explore the beam again.
Sort of did already when he was going backwards. You could see that the needle was tracing a it wasn't just going straight down to zero. It gradually went down to zero. So we kind of already saw the pattern. So this seems quite predictable, okay, in the sense that now there's a magnetic field and it's stronger on one side than the other side. But I don't know if that would make much
The
difference,
beam has been brought.
because what you're really saying is it's going to push more on south poles, push them away, and it would be attractive to north poles. So the north poles would be attracted, the south poles would be pushed away with the same intensity. And the weakness of the south pole is doing the same thing. It's weakly pushing and weakly pulling. So in a sense, it's still an even field.
Symmetrically, you notice.
So atoms that go in, say this is the north side. Atoms that go in with the north side facing this direction, let's say it's a south field, it's the strong one, they'll move in. If it's this way, then they'll be pushed out. And they'll be pushed out with the same intensity these would be pushed in. Because the south pole is attracting and repelling weaker, but proportionally. So that's just really the question. So if it comes in with any orientation in this direction, it's going to tend to move this way. Any orientation this way, it's going to tend to move that way. And that's exactly what you see. Now the trick is what's happening to the ones that don't do anything. Okay, so in this thing, there's some atoms that are just going straight through. Now the argument would be is those are the atoms that are going really fast. So even though they had an orientation north and south, they couldn't be affected because they were moving too fast for the field to affect them. The field wasn't strong enough to bother them because they weren't in it long enough. So again, another time issue. They have to be in the field longer to be affected by the field. So even though the magnet's 6 inches long, these things are traveling, could be very high speeds. I don't know, quarter of the speed of light or something. Very fast. And so the really fast ones are the ones that are still looking like a regular beam, like they're neutral.
Showing that cesium atoms are in fact magnetic and are deflected in either direction by the magnetic forces.
So it really is no surprise. I don't know why, if I put two regular magnets, north side and a south side, just regular magnetic field, and shoot it through, why wouldn't I get exactly the same result?
But let's see what happens when we increase the magnet current some more. Two cells give us about 5,000 Gauss and a gradient of about 6,600 Gauss per centimeter.
So now you've really increased the magnetic field. It's a lot stronger. So now even the fast atoms aren't going to be able to not be affected. So now you're basically saying there's not going to be anything left going straight through, because everything is a little bit this way or a little bit that way. Everything's tilted a little bit this way or a little bit that way, and so everything's going to have to choose a side. And that's
The
pretty
pan
much.
begins to deflect sooner.
And the volume would probably tell you something if they did the volumes of these loops to see whether they retain all of the original atoms or somewhere in these volumes. That would have been interesting, but they didn't give you that detail. But notice, nothing now is in the center. So none of the beam has remained intact. It's been split into two sections. Now I'd argue that's totally intuitive, totally consistent with what you would think would happen. If the magnetic field is strong, all the atoms get pushed. If the magnetic field is weak, some of them don't get pushed because they're going too fast.
But then right in the middle, where most of the atoms were before, there are now very few, and the rest come over here. The atoms have been deflected equally to both sides. As they pass through the magnet, half of them were forced in the direction of stronger magnetic field, and the other half.
So again, saying stronger and weaker is just kind of deceptive, because it's still consistent, and you're still pulling. You're just basically saying every time I pull stronger on the north, I'm pulling weaker on the south, and every time I'm pulling stronger on the south or pushing stronger, I'm pulling weaker on the north. So the two really do balance out. I mean, it ends up being symmetrical, even though the two sources are asymmetrical. The repulsion force and the attraction force of each individual pole is still the same. There's still just as much repulsion from the south, from this side over here. The coil over here is pushing south things just as hard as it's pulling north things. And the same is true for this south pole. Even though it's weaker, it's pulling and pushing the same amount. It's pushing on north and pulling on south the same amount. So the net is that it's really a balanced field.
Were forced toward weaker field. Let's increase again to about 10,000 Gauss per centimeter.
So the stronger you make the field, okay, so now they've increased it again. Now you're just saying you're going to push them even further. That's all. So you've got them separated with the strong field. You've got all of them influenced. And now you're just saying, yeah, let's influence them some more. Let's just push them further or pull them further. And that's it. So again, perfectly consistent with an intuition of just understanding it as a magnet being thrown into the field. And the fact is, if it has any tendency to be in this orientation, it's going to go that way. If it has a tendency in this orientation, it's going to go that way. I mean, completely unremarkable, frankly.
the two wings are separated and broadened still further.
So you can see that the key part that's different is out here in the fringes, where now you have a lot more atoms further out on the wire. The wire has deflected them a lot further. The magnetism has deflected them. They're being seen out here and out here instead of in here, and that's what you can see. You've just made it by making the field stronger. You've just pushed them further. No surprise at all.
And now there's almost no intensity in the center. We can show that by closing the beam shutter and making the trace again.
And the center is just about speed. So the center is basically just telling you the difference between these lines are just really telling you the speed. Okay, so there's a point where the fastest ones, even the fastest atoms, are going to be bent by the magnetic field, and there's a point where no, the fast ones will get through. And that's the difference between this up line and this down line.
Now, how can we go about accounting for these particular magnetic deflections?
Alright, so I've given my account, which is simple. This is not complicated, frankly, so there's no big surprise. But what would be nice to have is the chart for different magnetic fields. So show me the chart for a true north-south field, okay, where they are pulled. The pulling gets stronger as they get closer, all of that kind of stuff. Show me that field. I can't see how it could be much different, frankly.
We know that the atoms emerging from the oven have a random thermal distribution of speeds.
Alright, so that's what he says. They know. I don't know if they know it, but they probably did in some way or other test what that peak is made out of. So if you test it further, you find that some atoms get to the wire really fast, some atoms get there very slow. So I guess you just you open and close your beam with a certain speed, and then you can tell how much lag there is in the beam's width.
And are also randomly oriented. What would such atoms do if they were really little bar magnets?
It's hard to say whether they're truly random, just because you did put them through metal slits. You did do some stuff where certainly any charge on those surfaces could have changed their orientation a little, but who knows?
Like this one sitting in a frictionless air bearing.
So that's kind of neat, the little air bearing. So they shoot air, and then this ball is basically, floating on that air surface. Kind of a nice setup.
Each atom, while in the field, would oscillate very rapidly about the field direction.
Now that's just speculation about this oscillating. Like I said, we don't see the iron filings oscillate. So he's just saying that somehow if we get rid of all the friction, that somehow the momentum of orientation would be, it wouldn't be dampened out of the system. I would argue that the magnetic field will consume that oscillation. Now they don't really tell you what field they put this in. So is this in with just one coil on? What's the field? So I think they're just blowing air through this tube. I'm not sure. So that oscillation was completely a consequence of, Bernoulli and stuff. That's a whole different subject.
The range of angles depends on its original orientation. An atom like this passing through our apparatus would at the same time be pulled sideways by the field gradient. Its final deflection would be the result of a kind of average over its oscillations.
So again, he's saying weak field, strong field, and really it's a strong north side and a weak south side. So it's really, kind of deceptive. But the point is the south side is consistent and the north side is consistent. So it's repelling as much as it's attracting.
This curve shows the kind of beam shape to be expected in that case. One would find atoms deflected either way, but the curve is asymmetric.
So that's dealing with the fact that if the south field is weaker, it obviously can't pull as hard and it can't push as hard, so there should be an imbalance in the field. But I don't think that's a legitimate argument with the two coils on.
The compass needles are more likely to move toward the stronger field. But we saw that that doesn't happen. Even when our magnetic field was too weak to reveal the splitting, we saw that the deflection pattern of the beam was symmetrical.
Right, because you're still stuck with the truth that you're pushing on the two poles with the same force from both sides. So this side is pulling with the same force that it's pushing with. This side is pulling with the same force it's pushing with. So in truth, it can't migrate one side to the other side because the forces are the same. The repulsion is, as much as you might have repulsion here, your attraction is weaker. Vice versa. If you have attraction, your repulsion is weaker.
Now suppose that the atom's a little magnetic gyros like this one when we spin it. Comes nearer to the truth, for we know that there's an intimate connection between angular momentum and magnetic dipole moments.
No, so they say they know this crap. They don't know any of this crap. So this is just, again, they're contriving excuse to create spin, and it still doesn't work.
Atoms. This magnetic gyro has a stability. The angle between its spin axis and the magnetic field remains constant, even though the gyro precesses about the field direction.
Right, so that's all he does. He's changed wobbling into processing. So what?
Thus, even an atom starting out at a large angle to the field would remain with that large angle to the field. If our atoms were like magnetic gyros, randomly oriented, the beam would be spread symmetrically, as in this curve. But clearly this won't fit our data, because there'd always be a hump in the middle, however large the field gradient.
So that's the part where he's basically saying it doesn't matter how fast they're going now, because some of them are so balanced that they'd still go through the field without being pulled one way or the other. So he's saying you can't create this base at the bottom. But I would argue, of course, you can, because the fact is they're not doing all of this gyroing. And the fact is they're just either got a bias in one direction or they have a bias in the other direction. None of the atoms are perfectly oriented, perfectly perpendicular. Perfectly perpendicular basically doesn't happen. I mean, it happens this little tiny amount. Everything has a bias.
And so to
A pragmatic bias.
explain these data, we have to use a quantum model.
So that says so. Complete says so nonsense, in my opinion. No, you don't have to.
The atoms are quantum gyros, restricted to a few discrete orientations in a magnetic field.
So he doesn't explain whatever the quantum catch is that lets him have have it both ways.
With our cesium atoms, we see evidence for only two orientations, parallel or anti-parallel. The thermal distribution of speeds, of course, smears everything. Slow atoms spend longer in the field than fast ones and undergo bigger deflections, so we get lumps rather than sharp bumps.
Right, and that's exactly why you can change this center from an up to a down. Is because you just make your field stronger than the velocity.
Here's a curve calculated according to quantum theory, and it looks very much like our data. The agreement is still closer if allowance is made for the finite width of slit and detector, thus smearing the theoretical curve even further.
Yeah, blah, blah, blah.
When the Stern-Gerlach experiment was first performed in 1922 with a beam of silver atoms, no one knew what to expect, or rather, people did think they knew, but they didn't quite agree. Some thought the beam would not be affected at all.
So who would think that? Yeah, that would be silly.
Some thought it would simply be broadened, and
So yes, so some thought it would just do this little archy thing, fine. And again, you have to just apply the speed notion to understand the difference between this line and this line. It just has to do with speed. You've defeated the fastest atoms, and now even they have to succumb to the field. That's all that represents.
some, including Niels Bohr himself, thought it would be actually split. And even some of those who expected a quantum splitting were surprised at the hole in the middle, the complete absence of an undeflected component.
So you can't really say a splitting and then say the absence in the middle, right? If they're split, then that concedes the absence in the middle. How can a split not be defined any other way? If it's a split, it has to have the zero in the middle. I mean, damn. I mean, that's just word games there.
In the beam. This was a decisive experiment in the development of quantum theory.
And I would argue that it's decisive in no way whatsoever, and subject to vast, ranges of interpretation in terms of just understanding what an atom is, what its polarization is. And again, atoms could have more than one polar orientation. They could have north-north, south-south, and they got 3 dimensions, So there can be more than one polar surface. That is, they can look north this way, and then they could be north-south this way.
Now, before we end this film, let's do one more simple experiment.
So this one, I don't know what like I said, this has to do with playing all kinds of games about when they talk about, resetting an electron, and they're going to orient its spin in a certain direction. What they're really just saying is we'll just pick all the little atoms that are on this side because we know they're all pointed that way. And the atoms on this side are pointed that way. Yeah, that's not that miraculous either.
You'll remember that we have some movable jaws between the magnet and the detector. We'll insert one of these jaws so that it cuts half the split beam off.
So I guess the only thing interesting about this is that you do get a little bit of the, some of them go around the edge of the, the material, the blocking material.
Means that we could work if we wanted to with this beam of atoms.
See that? Whoop, a little bit.
All oriented in one direction with respect to the magnetic field. The placing of the jaws was not quite perfect in some sense. We could make it better. But most of the other beam is missing. Now we pull out the first jaw and put in the other.
So again, not all that interesting. So they're a little better this time, but they still got something of the other beam. So even though it's supposed to be 0 there, it's not 0. So that is sort of interesting. Well,
And we
near
get a beam
0.
of atoms all in the opposite orientation. This opens up the possibility of doing experiments on selected magnetic quantum states of atoms.
So they say quantum states, and all you're saying is the atoms are oriented this way. They have an orientation this way or that way. It's not a quantum state. It's just either the magnet's pointing north or the magnet's pointing south. I mean, jargon. Whoops.
In an atomic beam. It's a work which I happen to like. I began this film by saying that cesium atomic dipoles are as magnetic as iron. Here are
So he's just saying the atoms themselves, okay, when independent of each other, are ions. They're non-symmetrical.
data from this experiment that you can use to show that this is so. The magnet length is 12.5 centimeters. The distance from the end of the magnet to the detector is 50 centimeters. The oven temperature is about 400 degrees Kelvin. And the distance between the two peaks is 3.7 millimeters. When the field gradient is about 10,000 Gauss per centimeter.
Right. So all of that is just for the people who want to do some sort of math, I suppose. All right. So anyway, that's all, folks. So I would argue that the experiment is subject to simpler interpretation than the interpretations they wish to impose upon it, in terms of defending something like, they say this demonstrates electron spin. They use this experiment to prove that somehow electrons are dipoles. Now, even though he overtly is pointing out these are atoms and that these are dipolar atoms, they'll claim that this experiment is showing you dipolar electrons. That somehow electrons aren't just monopoles, that they're somehow a dipole and they're somehow being affected as a dipole, have dipolar functions. And there's just nothing in this experiment that actually says anything like that. So it's really quite annoying. Alright. I think we've accomplished the task. So, it's sort of an important. This experiment has bugged me for, I'll point out, years. Not that I didn't always suggest that, yes, this teardrop, right? If you took that image and you just flip it, double it, you have this teardrop kind of effect, right? And they always put it in this orientation, so which is kind of funny too. So it's always they often show it in this orientation, and yeah, it did seem a little strange, and but clearly completely, in my opinion, completely understandable, and that you're just measuring the effect of a magnetic field on dipolar atoms, and under this special circumstance where you're changing how fast they can move towards a magnet. That is, they're not feeling a strongly increasing field. Okay, something like that. All right. So till the next time, and such and so forth and whatnot. Yeah, I think that's enough.